I'm on a mission to make an unpickable lock. Lock companies have become complacent producing flawed designs. I want to make something that's not only secure, but designed with manufacturing in mind. In my last video, I went over the idea and made 2 working plastic prototypes. In this video, I'm going to improve the design, and by the end, we should have a working metal lock. This is an interesting topic, so watch that video if you haven't already. It's got some fun visuals and demos, but I'm going to do my best to summarize. Pin tumbler locks cannot rely on precision to be secure. Because of this, the setting, which is this movement here, and the testing, which is this movement here, have to be separated. Otherwise, there will always be a pin that binds first and can be pushed out of the way. This design separates the two by using wafers for setting and a second shear line for testing. Before I can dive in and design a shiny new brass lock, I want to talk about some learnings I had with a full-scale prototype. Besides friction, there are 2 related issues that I want to address. I also want to address them without adding any additional parts to the lock or complex features. First, since there are 2 shear lines instead of 1, it is very important for all the parts to be aligned well to allow the pins to slide smoothly. You may have actually experienced this before when you go to pull a key out of a lock and you have to jiggle it a little bit to pull it out. That's the pin sticking on the shear line. I've seen fancy locks use spring-loaded detents to align the core in the lock. In some ways, the watchdog pin is already a spring-loaded detent. Let's just swap out the watchdog pin for a watchdog pin with a conical tip, then spot drill the cammed surface, and boom, there you go. The core self-centers at almost no additional cost. Second, the mid-core could over-rotate as the lock resets if the watchdog driver doesn't drop. If this happens, the key may get stuck in the lock. My idea is we take out the clock pin and replace it with a longer clocking pin, and then we just add a hard stop so it just can't over-rotate. Pretty neat, huh? Now, while there's a lot of ways to make parts, the shape, material, and general tolerances of the lock point towards a method called machining. Machining is a subtractive manufacturing method where material is removed in small passes at high speed. Specifically, 2 subsets of machining called turning and milling are most likely to be used. Turning is performed by spinning the part and introducing a rigid tool to cut features, while milling is performed by holding the part still and spinning the tool. Ideally, these parts would be produced by a machine that can do both, so it can be done in one setup. Let's take a look at the design of the mid-core. It's not a coincidence that locks are made up of a bunch of cylindrical shapes. Turning and drilling are quite effective methods to create parts. The faces in green are created from turning operations. The features selected in blue are milled/drilled. As we look over the design, try to spot which features are turned and which ones are milled. Turned features will always be concentric with the main axis of the part, while the milled features will be everything else. Finally, let's take a look at the CAD. From the side view, we can see the 5 pin stacks and the watchdog pin. When the correct key is inserted, the pin stacks are raised so that the top shear line is free to move. Looking at the lock from the front, we can see the 3 main interactions. First, the clocking pin. As the core rotates, it picks up the clocking pin, moving the mid-core along with it. Then, as it returns back to center, it picks it back up. Second, the watchdog pin. It is lifted up as the core rotates until the clocking pin engages and the mid-core is free to rotate. Third, the main pin stacks. The wafers provide the first shear line, then the master driver interface is tested at the top shear line, and if those are at the right height, the lock is good to open. I want to take another look at this prop from last video, the 4 holes in a straight line. This prop is indicative of the imperfect world we live in. No part is perfect, especially when you're trying to make a lot of them. Fortunately, engineering has an answer to this reality. The answer is tolerance. Tolerance allows for a designer to specify a range of parts that would work for an application. As the tolerance gets smaller, the cost goes up, since the manufacturer must work harder to ensure the part is the right size. As the range gets larger, the cost goes down, as the manufacturer doesn't have to work as hard to keep parts within tolerance. Let's take a look at specifying the applicable tolerances between the core and the mid-core. In engineering, this clearance is known as an engineering fit. Different fits will specify how the core will move inside the midcore. Standard fits are organized into several types that are further organized into individual fits. Taking a look in the machinery's handbook, we can see a description for each of the fits. RC7, free running fits, seems like a pretty good jumping off point, as high temperature variations are something a lock might experience. Taking a look in the tables, under RC7 and the relevant diameter, we can see that there is a 2/1000th minimum diametral clearance. Our scenario, however, is a little more complex than a table in some book. We want to maximize the tolerance to keep costs low. We also want to ensure that the pins will interact and slide correctly at the shear line. Since there is also variation in the position of the pins, we will alter the height of the pins as we explore what works. Let's first start by lowering the pin stack down as far as we can. You can see the limit we run into is the upper wafer will become stuck on the edge of the core. From this lowest possible state, as the clearance increases, it gets to a point where the mid-core may not successfully pick up the upper wafer. Knowing that the mid-core must always be able to pick up the upper wafer, the two are locked at this maximum as the clearance increases. This continues until the point where the lower wafer may be grabbed by the mid-core because of the play in the two elements. From here, the clearance can be reduced to the point where the mid-core may not be able to pass over the lower wafer. From here, the two are decreased until there is no clearance. Combinations in this zone may work. However, I don't like the idea of the mid-core being able to grab the lower wafer, so it will be avoided. The minimum clearance per the machinery handbook table should be no less than 2 thou. Also, large gaps where the wafer may get stuck should also be avoided. This leaves us with the following region. To simplify the tolerances, we're going to reduce the region to a rectangle. This zone now needs to be divided between the core and the mid-core. I'm going to give plus or minus 2 thou to the core and plus or minus 3 thou to the mid-core. The core gets a slightly smaller tolerance because in general, external features can be cut more rigidly than internal features. Although we're not in control of the other side of the zone, I have statistically observed that the total length of the pin stack varies under 3 thou. That means that the other 4 thou are available for the position of the key. All right, let's get these tolerances on the drawing. I'm ordering these parts on Xometry. I like these on-demand manufacturing services because they won't shy away from single-piece orders. However, they will charge you an arm and a leg using their automated pricing engine, which, in all fairness, is pretty fun to play with and see what price breaks are like at higher order quantities. While we're waiting for the lock parts to arrive, I want to talk about this, the key. I've decided to key the lock with the KW1 keyway. This is a very common keyway, and there are at least 3 benefits to choosing a common keyway in this design. 1, you can easily get keys made. Locksmiths and key machines will always have KW1 blanks in stock. Very cheap. 2, common key, common pins. This means that you can buy pins very cheaply, whether it's for manufacturing or for a prototype. Another benefit is that locksmiths already carry these pins, so they would be able to rekey the lock. And 3, there's already machines and tooling out there to cut the KW1 keyway. Keyways are typically formed using a process called broaching, which has really high startup and tooling costs. So by using an existing keyway, we get to capitalize on that existing tooling. Sounds like the parts are here. And without further ado, the parts. They look beautiful. And they're even in tolerance. But now it's time for me to get them assembled. Take a look at this lock. Isn't it beautiful? But we don't really care about that. Let's see if it works. That's the most important thing, right? And pretty good key insertion for the amount of pins and shear lines there. I would say it's honestly just about as smooth as another pin and tumbler lock. But let's see if it opens, because that's the most important thing, right? And we have an open. All right. So, yeah, and the rotation is also very smooth, and I can feel that watchdog pin doing its job right there at the end. I don't know if you can see that, but anyway, I have a jig that I made for the lock to go into. So I made this jig to really show its operation. And can see it works as expected. Very cool. I also have this key, which is a different cut. So this key does not work in this lock, or should not work in this lock. You can see it goes in, but we do not get the full rotation. So there are a bunch of other small things that I would change if I made another iteration, but overall, I'm really happy with the lock. I really am happy with how this lock turned out. Get subscribed, because in the next video, I'm gonna be trying to pick this lock open. If you have any ideas about how you might be able to pick or manipulate this lock, please let me know down below and I'll be sure to try them out. Thanks for watching.